And hello guys, welcome back to our radiation heat transfer learning journal. So in the last video we were talking about heat transfer between, let's say, two surfaces, and we were looking for an expression for this little bugger here. Alright, so okay, the answer to this is found in the 1.7 of the Michael F. Modest's book. So let me just go through what he's discussing. Yeah. So all this stuff here, I'm just going to try and summarize in this video. So okay, let's consider two surfaces again, two arbitrary surfaces. Let's say this is dA3, and here is dA4. All right. So let's say these two. This is a black surface, so black surface. Okay, so what is the energy output of this black surface? All right, so let's do a little copy and paste. Okay, so again, the question is how to find IB. Right, so we kind of have this little situation, and what's the energy output? Total energy output. Total energy output. So this output is equals to the power per unit area times area. All right, and what is this power per unit area then? This is n squared sigma t to the fourth, and you times the dA3. So this, if you know, that is what we sometimes call EBT, dA3. All right, so this is from earlier. We kind of have this expression that we have here, EBT. Okay, right, I think this one was a little bit of a mistake, so just cancel this. You made a mistake there with the formulas. Okay, explain a little bit more later why this is a cosine theta with it, and that's something else, but okay. Anyway, we have a EBT times dA3. All right, this is the total energy output. And what's the other way to express total energy output in terms of intensity? Okay, so what is intensity? IBT, which is again this bugger here, IBT, is equals to power per unit normal area times solid angle. All right, so this power is none other than this EBT dA3. So I'll just put this like that. Power equals to IBT times normal area times solid angle. And what's the normal area? Normal area is equals to dA3 cosine theta 3. All right, so I'll just use the placeholder cosine theta 3 to represent. Okay, so we draw a line between these two, and we draw the normal up, and we just say this is theta 3. All right, that's the normal area, right? And solid angle, which is dA4 over r squared, dA4 cosine, okay, dA4 cosine theta 4. All right, cosine theta 4 over r squared. Okay, and what's another way to express this? If you're familiar with solid angles, then you should have this expression over here, as shown in the textbook. Sine theta 3 d theta 3 d sine 3. Okay, so You see this d omega equals to sine theta, d psi. So in this case, theta is theta 3. So sine theta 3 d theta 3 d psi 3. Alright? Okay. So anyway, I think there should be an integral here. Right? Because you're supposed to integrate over all the areas, or rather integrate over A3, or rather, yeah, there should be an integral here. Where is that integral? Okay, integrate over all omega. Okay, so you're integrating over all solid angles, and this is actually what d omega is. Alright, d omega equals to all of this here. Okay, so, and that is also equals to, the other way to put it is this. Yep, this is what the solid angle is like. So I need to integrate over theta 3. Okay, so what is theta? How do you integrate theta? We need to integrate from 0 to pi by 2. Okay. Okay, so, and we also need to integrate from 0 to 2 pi of this psi 3, right? So why is this so? Okay, so if we can just recall, all right, where's my mouse? I can see, there you go. The mouse is here. So let's use a bit of a thicker color, thicker kind of a thing. All right. So theta 3, it starts from here, goes all the way here. So this is from 0 to pi by 2. Right? And what is psi? Psi is the azimuthal angle. Psi 3. It goes from 0 to 2 pi. It's one full circle. Right? 0 to 2 pi. Alright, so always try and do this kind of a diagram drawing. It's much easier to see and visualize. So alright, so for pretty much now we are set. So we can just do some simple equivalence. This, alright, is equals to this. This is the total power coming from dA3. Alright. So dA3 is kind of independent of direction. However you consider theta 3, the area A3 is kind of constant, right? No matter how you consider this problem, dA3 is a constant. All right, so dA3 can be brought out of the integral, and you can kind of divide both sides by dA3. So dA3, we can divide both sides by it. I'm going to remove all the times in the multiplication symbols inside just to make it more neat, the expression more neat. And the other thing we note is that the other thing we need to note, according to Kirchhoff's law, black body radiation is direction independent. I'm not going to go through the proof here, but if it's direction independent, I can bring this up, because no matter or rather intensity, according to Kirchhoff's law, black body intensity is direction independent. I'm not going to prove it here, but all it says is that I can bring this out. Okay, I can bring this out. So we can just evaluate the integral as so. Alright, psi can be evaluated first, and this will just give you 2 pi. And if you plug this into Wolfram, alright, you plug this into Wolfram, you just get half. Okay, so you can just take my word for it, you can go and prove it yourself. Alright, whatever you integrate here will become half. Okay, I'm not gonna prove it. This is pretty simple integration. Yep, this simple integration. I've done it before. I'm not going to like do the full integration here, but we can take it like that because okay, when we plug this expression into equation 1.31, okay, let's not confuse you. Okay, so yeah, you just take my word for it that this is so. This is half, and 2 and half cancel out, and you have this expression. So now it looks like we have an expression for IBT, and that is just EBT divided by pi. Very simple. Okay, so we have this n squared sigma t to the 4th over pi. So now we have an expression for IBT, right? And what is this thing coming from? How do we get Lambert's cosine law? Okay, so but there's some confusion. There could be some confusion. What is this? Okay, so we have this Lambert's cosine law. And why is it different from, let's say, this? Why is there a cosine theta here and then there's a pi here? Okay, so now I'm going to explain that. Okay, this formula actually takes into account the direction independence. So what is this here? This is actually power per unit area per solid angle, right? And this is what this E in this case represents. Okay, this E over here is just power per unit area. There's no solid angle being like taken into account, so direction is not important in here. Okay, so what is this power per unit area per unit solid angle? Okay, yeah, it is this IR, this intensity into cosine theta. Why? Okay, let's see what this intensity is. This intensity here is power per unit normal area per solid angle. Okay, so these two kind of cancel out, right? Yeah, so these two kind of cancel out, right? So you have the power per unit area per unit solid angle times something. Okay, what is that something? Okay, the something here is, okay, let's see this, what's the relationship between area and normal area? Okay, let's see. I'll just put this here. All right, so let's say, or rather we'll just put this power per unit area per unit solid angle. We'll get rid of this little area here, so we'll just do power per solid angle, right, equals to E, whatever this expression is, times the area, and the area here is, let's say, the A3, right? And over here, if we want to multiply by the normal area is the A3 cosine theta 3, right? And what do we have when these two A3 cancel out? We have Lambert's cosine law. Okay, so this is different already. So this is where we get Lambert's cosine law from, because this one takes into account solid angle, whereas in this case EBT doesn't take into account solid angle. Alright, so hopefully that clears up the confusion. What is the difference between this cosine law? Why is this having a cosine and then this not having a cosine? Alright, so if we were to bring this back into this Q, alright, substitute back into our heat transfer expression, we'll have this. Alright, we'll just have this expression. Oops, why is it gray? Oh, okay. We'll substitute IBT equals to EBT over pi into here. Alright. So this is how we find this little IBT over here, the black body intensity, in terms of something much more simple, especially for black surfaces, right? So yeah, now we know how to find out our little IBT. We can refocus back on this geometric factors here, the theta 1, theta 2, A1, A2, right? So that will be in our next video. Thanks for watching. I'll see you guys next time. Bye bye.